Hi everyone, my name is Raquel Urtasun and I'm the Chief Scientist at UberATG, as well as a professor at the University of Toronto. In this talk, I'm going to review the latest work that we have done on interpretable neuromotion planners. A very popular approach in academia to autonomy is to train a neural network for the task of driving. The input to such a system is a set of sensor measurements, for example, LiDAR or images, and the output is the information necessary for the self-driving car to drive, for example, steering command and acceleration. The advantage of such an approach is that it is very easy to get a prototype with just a few lines of code. Furthermore, the system is trained for the end task, which is the task of driving. However, this paradigm has several key disadvantages. It is difficult to incorporate prior knowledge, and thus make the system respect the rules of traffic. It also has no interpretability, which poses a problem for the system's validation and safety. An alternative is the traditional software stack, which is composed of a set of modules executed one after another. Every fraction of a second, the vehicle senses the environment. This is illustrated here with a bird's-eye view of the LiDAR point cloud. The first task is then to localize the vehicle with precision of a few centimeters. This is done not only to route the vehicle to the desired destination, but also to utilize high-definition maps as prior knowledge for subsequent tasks. The perception system is then responsible for estimating where the objects are in the scene, here depicted with rectangles for vehicles and circles for pedestrians. The prediction system then takes the output of perception and estimates the potential trajectories that the actors might take in the next few seconds. Then the motion planning module focuses on a region around the self-driving car and estimates the safest maneuver towards the goal that the vehicle should do in the next few seconds. The control system then ensures that the trajectory we intended to follow is the one that is executed, as there might be deviations due to unaccounted factors such as friction and simplistic vehicle dynamics. This full process is then repeated every fraction of a second, typically every 100 milliseconds. The advantage of this approach, or this type of paradigm, lies in the fact that we have interpretable intermediate representations, and it is easy to incorporate prior knowledge. However, reaction time is typically large as computation adds up. Furthermore, developer productivity is very low, as any changes done in one part of the stack will affect the entire stack, and engineers need to manually adjust their algorithms to account for those changes. Furthermore, the different models are not trained for the end task, and thus improvements in model performance do not translate to better driving. Our vision, which is different from any other competitor, has the advantages of both end-to-end and traditional engineering approaches, but without inheriting the respective drawbacks. In particular, we believe in having a single AI system that can automatically adjust itself to any changes, thus increasing significantly developer productivity. As computation is now shared across modules, the resultant reaction time is also much lower. Furthermore, we produce interpretable intermediate representations and allow for the incorporation of prior knowledge, for example, to guarantee that we follow the rules of traffic. And finally, since our approach is trained for the end task, every improvement results in better driving. Our first attempts towards this vision focus on developing approaches that can do joint perception and prediction. That is 2/3 of the software stack with a single AI algorithm. Fast and Furious was the first such approach that appeared at CVPR 2018. The input is a history of previous LiDAR sweeps. Using the pose of the SDV at different time steps, we can project past sweeps to the current coordinate frame. We can then voxelize the point clouds into a bird's-eye view tensor with 4 dimensions: height, width, time, and depth. Now we can run 3D convolutions using depth as features to fuse the spatiotemporal information. Once the time dimension has been reduced, we can predict the output with 2-dimensional convolutional headers. For each pixel in the output map, we can predict a classification score and a series of future waypoint regulations. To obtain the final detections, we threshold the scores and apply no-maxima suppression. We then obtain a single feature trajectory for each actor by indexing the regression tensor at the positive locations of the classification after NMS. In this video, we show the LiDAR point cloud together with the detection scores, bounding boxes, and the short-term motion forecast for 1 second into the future. The vehicles are color-coded according to a heuristic tracker that matches detections to previous motion forecasts as a post-processing step. You can see here how difficult is the task of driving, where we need to localize very accurately a very large number of traffic participants, all in a fraction of a second. As a disclaimer, I'm going to give a full talk at a different workshop on our efforts on joint perception and prediction. So I point you all to look at precognitions in the future for more information on this. However, in the following, today I'm going to talk about interpretable neural motion planners, which is the future of where we see autonomy going. I will present 3 different efforts in this direction. Our first work is the end-to-end interpretable neural motion planner published at CVPR 2019. It uses a deep neural network to produce a learned cost volume and improves the performance of the deep network with auxiliary detection and prediction tasks. Later, we proposed DSDNet, Deep Structured Self-Driving Network, which further improves performance and interpretability, but outputting non-parametric multimodal predictions and planning condition on these predictions. The third work investigates how we can bypass detection post-processing, which may lose useful information. We propose perceive, predict, and plan, safe motion planning through interpretable semantic representations, where we replace instance predictions with an instance-free semantic occupancy representation and use learn interpretable planning costs over that to produce planning. Now, let me briefly explain the main idea behind each of these approaches. The end-to-end interpretable neuromotion planner is our first attempt towards this direction. It takes LiDAR and an HD map as input and jointly outputs detection, prediction, and planning results. For planning, the model produces a learned planning cost volume, which will then be used to generate a planning trajectory. As you can see on the top right, the learned costs can nicely navigate our ego car to follow the lane and avoid collision with other cars. Let's have a look at how the model works. The input to our model is raw sensor data in the form of LiDAR point clouds and an SD map, which are fed to a CNN in order to extract useful features. To produce interpretable representations, our model outputs detections on predefined anchor boxes. It also predicts each actor's future trajectory simultaneously. Next, we conduct planning. The model utilizes a simple deconvolution network that takes the backbone feature map and outputs a cost volume. The value of each pixel in this volume represents the cost for the ego car to be at that location and future timestamp, where different timestamps are encoding with different channels. Of course, lower cost regions are preferred. Here we highlight a low cost region in green. The purpose of this volume is to find a low cost planning trajectory. To see how it works, we show a zoom-in view of this volume. Again, different channels encode the cost map in different timestamps. And for an arbitrary trajectory, its cost can be easily computed by first indexing the volume at the appropriate temporal and spatial locations, then summing them together. During inference, we use a physically valid trajectory sampler to sample a wide variety of trajectories. These trajectories are guaranteed to follow vehicle dynamic constraints. We then evaluate the cost at each trajectory using the cost volume, and select the minimum cost one as our final planning output. Importantly, all computations from raw data to the final trajectory can be done in a few milliseconds. We train our model end-to-end with a multitask loss, including detection, prediction, and motion planning losses. For detection and prediction, we use standard classification and regression losses. For planning, since we do not have ground truth supervision for the cost volume, we utilize imitation learning and encourage trajectories to have low cost if they are close to the expert demonstrations. We also penalize trajectories that collide with objects or do not follow traffic rules. We evaluate our approach in our challenging ATG4D dataset. This dataset contains over 1 million frames from more than 5,000 snippets collected from multiple cities across North America. It provides prompt clouds from a 64-beam LiDAR sensor and high-definition maps. It contains very challenging urban scenes with many actors, making it interesting for interactions. Here we show our results. Compared with the state-of-the-art, the model achieves on par or better detection and prediction performance at the time of publication of the paper. More importantly, as we can see in the figure, our planning results have a much lower collision and line violation rate, which indicates safer planning. Let's look at qualitative results now. Our model takes LiDAR and HD maps as input and outputs detection, prediction, as well as the motion planning cost volumes. We highlight low-cost regions for different time steps using different colors. Our planned trajectory is shown in red, and the ground truth trajectory is shown in blue. As we can see here, it follows the lane perfectly. Note that our cost volume captures multimodality. In this case, we can either go straight or change lanes. When approaching an intersection, we can either keep lane or turn right. We can also handle blockage. The cost volume shows a preference to lane change in order to avoid collision. Here are two examples of super nudging in heavy traffic, which is a very complex maneuver to do in self-driving vehicles. As shown in MMP, sharing computation among all three tasks allows us to perform full inference within a few milliseconds and also maintain interpretable intermediate representations. However, there are still two major weaknesses of this work. First of all, the future is at times very uncertain. For instance, for the highlighted car, this car could either turn right or go straight. Moreover, different actors interact with each other and follow traffic rules, such as yielding and not colliding. Therefore, a multi-agent prediction with calibrated multimodal uncertainties is necessary for safe planning. Second, although NMP is able to predict the future, its planning model is not explicitly conditioned on the prediction output, which may cause some inconsistencies during the planning and the prediction models. To address these limitations, we propose DSDNet, a deep structured neural motion planner that jointly reasons about perception, forecasting, and motion planning. Specifically, our method has several advantages. First, computation is shared between models. Second, our method explicitly models socially consistent multimodal uncertainties in the future trajectories of the traffic participants. And finally, our learning-based planner leverages the power of deep learning and takes traffic rules into consideration, as well as in order to guarantee safety. Now, let's have a look at how our model works. Given later point clouds and an HD map as input, as before, we have a neural network to produce backbone features, which will be shared across all our models. We first use these features to predict detection results. For example, here we have 3 vehicles that have been detected. Our next step is to predict the future behaviors of all actors, as well as their uncertainties, which are shown as colorful regions in the figure below. Here, different colors mean different future time steps. Predicting these uncertainties is not a trivial task, as we expect to predict a multimodal non-parametric distribution which can capture complex situations. More importantly, the behavior of all actors should be socially consistent. For example, they should not collide with each other. To have an efficient representation for this non-parametric distribution, we first sample a set of dense, diverse, and physically feasible trajectories for each actor, and then build a probability distribution over these trajectories. More specifically, we use a neural network together with the backbone feature map to predict a unary energy for each trajectory. After normalization, these energies will provide us with a probability distribution. By doing this, for each actor, we have an estimate of the future. However, the produced probabilities do not guarantee socially consistency, as shown in the red circle, and it is hard to encode human knowledge, such as avoiding collisions, within our deep learning-based framework. Therefore, in order to model these interactions, we model each object as a node in a probabilistic graph, and have the edges encode our knowledge about their interactions, such as collision avoidance, yielding, etc. For example, For every pair of actors, we can evaluate a pairwise energy. In this case, since the actors' actions are socially consistent, we have a low pairwise energy. In contrast, here we have high pairwise energy since the actors collide. Then we conduct an inference process using loopy belief propagation so that high energy inconsistent scenarios have overall low probability. Finally, our model plans a safe trajectory for the ego car by considering the current situation and other actors' future behavior. Similar to NMP, we formulate planning as a cost minimization problem and solve it by first sampling trajectories, evaluating the cost of each sample, and then picking the minimum cost trajectory as our planning output. To compute the cost of a given trajectory sample, we also use a neural network to evaluate its unary cost. For example, an out-of-road trajectory will have high cost. However, this learned cost does not fully utilize the benefits of our predictions. Instead, we hope that planning can explicitly minimize the expected collision rate given our prediction results. Recall that our predictions are given as distributions over discrete trajectories. Therefore, we can easily compute an expected collision rate using a weighted sum. As shown here, the pairwise cost will be high if an ego trajectory collides with other actors, and low if it does not. Finally, we combine unary and pairwise costs and find the minimal cost trajectory among all samples. This gives us our final planning output. Here, we first report our prediction performance. We compare our multimodal socially consistent prediction method against several state-of-the-art methods on a number of datasets. Here we show results on two publicly available datasets, Nuisance and Preco-Carla. We achieved significantly better prediction error. Our method also achieves a near zero collision rate among predicted trajectories, which corresponds to more realistic human behaviors. Here we show our planning results. Again, we compare against an end-to-end imitation learning method, as well as our previous NMP method. Our DSD approach achieves significantly better performance in terms of collision and lane violation rates. This is due to the fact that now our model explicitly considers multiple future possibilities, and then plans a safe trajectory that is compliant with other actors' future behavior. Now let's see some qualitative results. In this figure, each blue box represents an object, and its dotted line represents its most likely future prediction. We visualize the model's uncertainty estimates with a dense color map. Different colors represent different times. This is the uncertainty at 1 second into the future. This is 2 seconds into the future. We can see that our predicted uncertainty becomes more spread out as the future is more uncertain. Here is 3 seconds into the future. Our algorithm is able to capture all the possibilities for the car approaching an intersection. This is a good thing. It suggests that our motion planner will take all possible features into consideration when planning its trajectory, not just one as before. Here is one more result of motion forecasting. We can see that for far away and turning objects, we are more uncertain of their future. On the other hand, for objects that are going straight along the lane and close to us, our model is quite certain. Next, let's see some planning results. Here we show a scenario in which our ego car follows a curved lane very well. This is a turning scenario. Here you can see that our planned trajectory is smooth and follows the lane structure very well. This is a situation in which a parked car blocks the ego car lane. Thus, our planner nudges around the parked car to avoid collision. Here's a short demo. As you can see, our model nicely captures multimodality, especially for vehicles that are approaching an intersection. When a vehicle is driving on a straight line, our model is more certain about its direction, but a bit uncertain about its future velocity. Here is an example where we perfectly predict that the leading vehicle is stopping and we plan a nudging trajectory to avoid collision with the parked car. This shows that our model can follow the lane perfectly. So far, we have discussed two efforts on how to improve interpretability for end-to-end neural motion planning. Both of these works detect surrounding actor first, and then conduct planning based on detection results. For example, in this case, the self-driving car situated in the bottom will know a coming vehicle is crossing its left turn lane, and thus will yield to the car. However, detection requires post-processing, and only reflects an actor if its detection score exceeds a certain threshold. But if the detection score becomes below that threshold, and then what happens when the ego car misdetects the vehicle? This might cause a severe collision, which of course we don't want to see. We tackle this issue by designing a novel end-to-end approach that perceives, predicts, and plans. The overall idea is very simple. Rather than performing object detection and then predicting trajectories for each object, our model directly generates semantic feature occupancies. Furthermore, the occupancy forecasts are scene-based and instance-free, and hence our approach does not require thresholding of detection scores or performing NMS, thus increasing safety. The planner uses these non-parametric spatiotemporal occupancy maps along with other interpretable costs to plan a trajectory that is safe, comfortable, and respects traffic rules. Note that the entire model can be trained end-to-end since all the components are differentiable. Let's dive a bit deeper into the exact intermediate representations we use. We consider vehicles, pedestrians, and bikes as the classes we want to predict their occupancy. Note that it is easy to extend this to other classes in the future. To make the representations more interpretable, we should devise them semantically as shown in the hierarchy. For pedestrians and bikes, we only differentiate between visible or partially visible, meaning that there are one or more LiDAR points on their surface and occluded. For vehicles, we should divide them into park, on conflicting lane, oncoming traffic, on the route, occluded, and others. This subdivision allows us to learn different weights for the motion planners of cost, corresponding to different subcategories. For instance, we do not need to keep the same safety buffer if we know a car is parked than if a car is in a conflicting traffic. Note that we assume vehicles, pedestrians, and bikes to be independent, since we can find cases where a small region of space is occupied by more than one class. For instance, a pedestrian getting out of a car. The subcategories within each root category are considered mutually exclusive. In the drawing, the colors of the occupancy represent their semantic class. We represent two pedestrians that are visible, a car that is on the route, and a car that is on a conflicting lane, and a visible bike. Similar to previous methods, we take a history of voxelized LiDAR strips and a raster map of the scene as input. We extract LiDAR and map features with a two-stream CNN and fuse them by concatenating them and adding a subsequent CNN. Finally, a recurrent occupancy update predicts the semantic occupancies into the future. As you can see, there is no processing at the actor level. This is another advantage of our method, since the computational cost does not increase in more cluttered scenes, which is important for real-time applications like ours. Let's dive deeper into the recurrent occupancy update. To obtain smooth occupancies over time, we leverage a special memory and a CNN-based update that only predicts the residual with respect to the previous occupancy. The planner samples a set of trajectories. A cost function is used to evaluate each trajectory considering different aspects of driving. The best trajectory is then selected for execution. The spatiotemporal occupancy maps are used to penalize trajectories that overlap potentially occupied regions. We use the map data to, for example, penalize trajectories that are not close to the lane centers or violate boundaries. Another aspect of driving that is included in our cost function is the route. Trajectories that are moving towards the lanes that eventually diverge from the route are penalized. We also take into account the smoothness and comfort of the trajectories in the cost functions. For example, trajectories that are turning at higher speed will cause large lateral acceleration and are not pleasant to the rider. Such trajectories get penalized as well. So as you can see, the trajectory cost function in our planner considers various aspects of driving. The relative importance of these subcosts are learned jointly with the rest of the pipeline. Here are some quantitative results for open loop experiments. That means that we enroll the predictions and a motion plan for 5 seconds into the future without replanning. In other words, in these experiments, the SDB does not get any further observations within the future horizon of these 5 seconds. We compare our method to ACC, which is a car following model, imitation learning, which directly outputs the ego trajectory from the fused feature volume in the model, and the neural motion planner that we were talking about before. We also include a model that detects objects and predicts multiple trajectories for them that are explicitly used in the planner's cost function. The results show that our proposed model is much safer than the baselines. For example, we get 40% less collisions at the best baseline throughout the 5-second future horizon. Once again, these are open loop experiments where the SDB does not get observations during the 5 seconds interval, and the rest of the actors do not react to our actions. Also, the generated trajectories of our model are more similar to the driving behavior of humans. Here is a video that shows examples of predicting semantic occupancies and open loop plan trajectories. The semantic classes are color-coded according to the legend on the top right. The empty boxes indicate ground truth objects and SDB. Our model is able to capture multimodality of future occupancies caused by each vehicle. The generated trajectories avoid occupied regions and stay within the lanes. The model is also able to pick occluded regions indicated by cyan color. Let me play this for a little bit so that you can observe more scenarios. And in here we are doing pedestrians, cyclists, as well as vehicles. The previous results are from open loop experiments, meaning that the current self-driving vehicle plan does not affect the world in future timestamps. To evaluate the closed loop performance of our method, we use our in-house simulator, which we are observing here in the video. Our closed loop simulator leverages our own state-of-the-art LiDAR simulator, LiDAR-Sim, that has just been published at the CVPR, and that you can see as an oral section during the conference. The simulation loop runs at 10 Hz. In each iteration, first the LiDAR sensor is simulated to generate a point cloud. Then the autonomy model plans a trajectory using the generated point cloud on the map. And finally, the state of the world is updated based on each object's planned trajectory. Note that the actors other than the SDB can have their own trajectory planning logic or use a predefined trajectory that is not reactive to the environment. The video that you were showing showcases an example of this closed loop execution, where we can see that the vehicle is basically ACCing to traffic. We then run 80 challenging scenarios, each for 10 seconds duration with our closed loop simulator. Each scenario has a subset of the yellow vehicles shown in the left image. These vehicles are initialized at various speeds and starting locations that are in conflict with the SDB route, particularly designed to test the safety of our decision-making when facing critical situations. Furthermore, they are not reactive to the environment and hence non-compliant. We collected various planning metrics as shown in the table. We compare our method to a method that detects objects and predicts trajectories. The results show that our end-to-end planner is much safer and generates significantly more comfortable trajectories. To summarize, we have explained how we can learn end-to-end motion planners that can directly output trajectories directly from the road sensor data with intermediate representations for perception and prediction. This enables shared computation among the different tasks of the autonomy pipeline and ultimately decreases the reaction time of the SDB. Moreover, we show that our models can plan trajectories for the ego vehicle that are consistent with the predictions for the other agents in the scene by taking this into account in our motion planning costs. On top of that, we propose an instance-free semantic occupancy representation that avoids information loss between perception and downstream tasks by removing the need of discrete decisions such as thresholding or NMS in object detection. Finally, we have shown that we can still make use of interpretable cost functions in the planner that encode our prior knowledge about driving and are interpretable. This is an extremely exciting direction of research, and I hope that many of you will be working on this in the future. Thank you.